As with any rule, there are always exceptions. And that's what science is. It is looking for patterns, looking for predictable outcomes. And then when you find out that something doesn't happen accordingly, it's explaining why something like this happens. So typically we fill everything according to this off-bow diagram. This is our off-bow diagram, where on the one that I provided, you see that you have the lowest energy level here and the highest energy level here, and these are all evenly spaced apart. Basically, I just took one line, then the next line, then I tabbed over to the 2P, then the 3S, and then I tabbed over from the 4S over to the 4D. But these are all the next lines on um, on Microsoft Word. And then you'll see that in real life, these values are not as far away as they seem. So in real life, the 4S is here, and then right here is the 3D, and then up here is the 4P, then you have the 5S, and then right next to it is the 4D. So there is this uneven increment between them. So when scientists look at the electron configurations for some of the elements, like for chromium, which is number 24, typically you would fill it this way with the off-ball diagram. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And this is the off-bow version, not the rewritten one. Okay, so what they found is that there's a certain amount of energy that relates to having the d orbital 4/10 of the way full, and this is the 3D orbital, this is the 4s, and this is the s orbital that is 2 for 2 completely filled. Okay, so there's a certain energy signature that this translates to in light and um, in energy, which the next couple of videos will start to talk about. But what they found is that this amount, let's say it's X amount of energy, is not what actually happens. It actually has less than X's energy. And it looked more like something like this energy quantum or bundle, and that is 4s1 3d5. It still has 24 electrons, just like this does, but what happens because the um, 3D and the 4s are so close to one another, it actually takes less energy for this electron, which is right here, to say, oh, I want my own room. I'm going to spread out. Because remember, electrons are all negatively charged and they all repel one another. And these orbitals are overlapping and so close that it actually looks more like this. 4s1, 3d5. So instead of being 4s2, it takes one away from here and adds it to here. Okay? So it takes less energy to half fill these 6 rooms, these 6 orbitals, than it does to fully fill one and have one 4/10 of the way full. Okay? You also see something similar for copper. Um, because it has that 4s2 3d10 or 3d9 version. So this last electron right here moves over to here, and it takes less energy to fill this d orbital than to get smushed into this s orbital. I guess it has more room to move out and around here. So it still has 29 electrons here. All right, so you'll see that these guys all add up to the same number, 29 electrons. But this happens with columns 6 and 11 on the periodic table. So the group 6 would be for your chromium and your molybdenum. Group 11 would be for your copper and your silver. And it happens in other places also, but those are the main places that you see this occur. And it occurs because it takes less energy to spread out than to force its way all filled into this 4s energy level. Okay, so if you ever see chromium, copper, molybdenum, silver, it happens here. It sometimes happens in the f orbitals also when you start, double and half filling all of those f orbitals. So it really is some tricky parts for the transition metals and the inner transition metals as well. Okay, so that's a nice little exception to the Aufbau principle that you guys need to take into account.